Okay, so I think we're almost done with the chapter. Let me share screen. Okay. Then, so we were looking at the Eddington approximation. Good. Let me close the door. So, I'll very briefly refresh your memory about these moments of the specific intensity field. So moment 0, mean intensity, moment 1, which would be the radiation flux, and moment 2, which is related to the radiation pressure. The idea is, in the Eddington approximation, to assume that the specific intensity field is nearly isotropic, and so we expand the specific intensity field to first order in the cos of theta, which would be like an expansion in a multiple expansion to first order. So this is the monopole, and this is the dipole. The idea then is to express the moments of the specific intensity using this expansion. So we plug in this expansion into equation 63 for the moments, and we obtain that the moments are related to these coefficients. Okay. So I just realized that I'm missing a new here. Maybe I'll fix it directly. And the interesting thing is that for the Eddington approximation for a dipolar field, we have the same relationship as for thermal radiation between the radiation pressure and the mean intensity. Okay, so that's interesting. And that is the root of the Eddington approximation. Okay, so the idea is to say that if the field is nearly isotropic, it's not quite a thermal radiation field, it's only all we require if it's close to isotropic. Okay, so if it's close to isotropic, then equation 65 should hold to first order, but to some degree of approximation. Okay. And so when we impose this relationship between the second moment and moment 0, we are using what's called the Eddington approximation. This is the Eddington approximation. It is a closure. It is a closure relation in a multiple. In a multiple expansion, which is equivalent to a moment expansion. So I think I expanded on this in the last lecture. So this Eddington approximation is a closure relationship. The point here is that we will use then this relationship to write an equation for the mean specific intensity. The only equation we have at the moment is the equation of radiative transfer, which can be cast into this form, equation 67, and for plane parallel geometry. Okay, plane parallel geometry. So this is okay for a slab in general, but also for anything that's close to plane parallel, like an atmosphere. And atmospheres are okay. The atmosphere of planets, of stars, are all around, you know. But if you look at them in the vicinity of one point on the sphere, then it looks like a slab, really. Okay, so that's why atmosphere are usually modeled as plane parallel geometries. And so this is the form of the radiative transfer equation. Of course, this is an integral differential equation because the source function here contains the mean intensity field, which is an average over I nu. Okay, so I think we saw this last in the last lecture through a question by Pratyush. Okay, we remembered that the source function includes the mean intensity, which is an average over I. So here there's an integral of I in here. So that's why I say this is an integral differential equation. Okay. Now the trick is to take moments on this equation. So we are taking moment 0, moment 1. Okay. And this yields then relationships between the moments of specific intensity. Okay. So that's interesting because if we look at here, like look at equation 67, this depends then on the coordinates, on the vertical coordinate would be z through the optical depth tau. You know, this is a change of variable to go from z to tau. And it also depends on direction. Okay, because I depends on position and direction. Okay, well, let's remember here that we have this field. So the field is dependent on direction and on position. Okay, this is plane parallel geometry. So this is Z. Okay, and we are assuming that everything is plane parallel. Okay, so these are planes with constant physical quantities. The only I mean, the symmetry in x and y is what I mean. Okay, so when we take moments of this rigidity transfer equation, I take moments on equation 67 here. Okay, then we have equation 68, which no longer depends on mu. It only depends on position. Okay, so when I take moments, either moment 0, 1, 2, what have you moments, we have equations that do no longer depend on direction. So this is what I mean by a formulation in terms of moments. We could this is a possible way of solving a differential equation. I mean, it's a technique to solve differential equations. You do a moment expansion, but this expansion normally goes to infinity, right? You normally take moments. Here I'm taking simple moments with only averaging mu, but you could use a more fancy expansion using an orthogonal polynomials, not just mu or mu squared or mu cubed, but orthogonal polynomials, and that would give you, like the polynomial expansion. So they're related, okay. But here we're staying with order 1 only because we'll be using the closure relationship. And so we saw this last time when we take moment 0 and moment 1. We get to equation 70 by using the Eddington approximation. So this is the Eddington approximation. So K nu is 1/3 J nu. Okay, we just saw it. It holds for thermal radiation. It also holds for a dipolar intensity field. And we are assuming that this holds when we use the Eddington approximation. Okay. So again, the Eddington approximation is this relationship between the radiation pressure and the mean intensity. Okay. Okay. So if we replace K equals 1/3 J, okay, then we have how did we do this? Oh yes, okay. So we replace H here. So I use equation 69. I have H is the gradient of K, and I plug it in there. You know, so in equation 68. So H is the gradient of K, and I have the second derivative of K here. But then I use the Eddington approximation to replace the k that would come here on the left-hand side with j. And that's how I get 1/3 second derivative of j, okay? So this is the result, and we have a single equation, a single differential equation for the mean specific intensity. The mean intensity goes into the equation through, it's in there, but it's also in S, okay? So we can rewrite this equation in terms of the albedo. So instead of using the full expansion here in terms of the source function, I replace with I mean, let me, where was it? I think maybe it'd be good to see this again, the expression for the source function. Can I find it easily? Yes, it's in there. So this is it. This is the source function. Okay, so we have so S nu is J nu related to absorption plus alpha scattering J divided by total alpha and total alpha here. Okay. And that is really, I think it'd be useful to add here the expression for the so the Planck function is related to J nu absorption divided by alpha nu pure absorption. Okay, and the so I need to and can write then the S nu as alpha nu absorption divided by alpha total times the Planck function plus alpha nu scattering divided by alpha nu total divided times J nu. Okay, so we can rewrite this in terms of the albedo. Where was it? The albedo. That's it. It's here. Okay, so we define an epsilon as alpha nu absorption divided by alpha nu total. Okay, and so that would be epsilon. And this one here is, I think, 1 minus epsilon alpha nu scattering divided by alpha nu. I think it's 1 minus epsilon. It's then so this cancels with that one, and we have 1 minus epsilon. Okay, so that's how we write the source function for isotropic scattering. Okay, that's the source function for isotropic scattering. I replace this expression here in equation 70, and I get down to equation 71. Okay, So that is, it's well, it's what we just said. It's a second order differential equation for J nu, where we need to specify the physical conditions only. I mean, once if we have the temperature field and the optical properties, then we can solve this equation for J nu. Then we'll have J nu. Okay, and then we need to from J nu, we need to get this specific intensity field, which is what we really want, and that requires solving yet again the radiative transfer equation, but this time we have the source function because we have J nu. Okay, two differential equations here. Okay. Okay, so in order to solve this differential equation, we need to apply boundary conditions. So if you pay attention, we have here, okay, this is nice. This is a differential equation for the mean intensity, but what are the boundary conditions? Because I mean, it's not so easy. It's not so simple, right? I mean, if we have so this is Z, and imagine we have like this uniform slab here from 0 to L, and suppose that there's nothing else in the universe, right? So only this is a shiny uniform slab, okay? So anything that goes from here, I plus, if you want, the coordinate 0, that would be no radiation field, no incident radiation field. And it would be the same for radiation coming this way, okay? So we know that I minus in this direction should be 0. Okay, so from the same notation, I'm just trying to say that this is 0. Okay, we can guess it would be like this. However, we know that this is going to shine. Okay, the slab is going to shine in different directions. Okay, and this is going to emit, and that is not 0. Okay, so what is J of 0 and what is J of L? What are the boundary conditions? It's not so simple. Okay, so in order to find those boundary conditions, we use the two-stream approximation. So in the two-stream approximation, we assume that the radiation field goes along 2 cones. This is what we saw last time. Okay, so these are 2 cones going upwards and downwards. Okay. Now this is not a mildly anisotropic radiation field. It is a strongly anisotropic radiation field. Okay. Normally, this is not what we would call. This is not a situation where we would be using the Eddington approximation. Okay, it's a strongly anisotropic radiation field. However, if we calculate the radiation intensity moments, okay, so you directly evaluate the moments on equation 72, you obtain this result. Okay. And so it turns out that here, the radiation pressure is indeed 1/3 of the mean specific intensity, same as the Eddington approximation, even though this is a completely different case, okay? But it turns out that mathematically it works. Mathematically, it gives the same relationships, okay? So we see that the 2 streams fulfill the Eddington approximation. In mathematical terms, it doesn't mean, I'm not saying that the 2 streams are not anisotropic, they're very strongly anisotropic. It just turns out that we can use the same relationship, which is valid exactly for the 2 streams. And of course, the 2 streams is also a possible specific intensity field. And the specific intensity is described by the radiation transfer equation. Okay, so this is the radiation transfer equation. Now, 2 streams are solutions of the radiative transfer equation, and they also fulfill the Eddington approximation. Okay. Therefore, they also fulfill equation 71. The two streams are also solutions of equation 71, which is the equation we're searching boundary conditions for. Okay. Oh, Pratius, go ahead. Just no need to raise hands, just interrupt me.
Okay. Professor, so in the book, there is a line which says that it is assumed that the entire radiation field can be represented by radiation traveling at just two angles, which is like cos theta equal to plus minus 1 by root 3. So why is it so? Uh, can't that cone have a bigger angle or or a smaller angle? Why that value? Why that exact value which says, which covers the entire radiation field? That is, I'm not able to understand fully.
Okay, Pratiush. So this is a mathematical trick. Okay. I don't think that there would be any possible situation in nature where we would have a two-stream really specific intensity field such as this one. We'd have to design an experiment to approximate it, you know. But I think that your question is on why this angle specifically. Why do we choose this angle specifically? Okay. So the
Yeah, and we also say that it covers the entire radiation field. So first we choose this angle, and then we also add to that these two angles cover the entire radiation field. Why?
it covers the entire. Second part, I think I might have misheard. So it covers the entire.
So I will just read out a paragraph or just a phrase from the book, which says that to solve the boundary condition. So they say that this can be done in several ways, but here we use the two stream approximation. It is assumed that the entire radiation field can be represented by radiation traveling at just two angles, which is cos theta equal to plus minus 1 by root 3.
Yes.
So
So Pratish, so yes, it's that paragraph. If after the equations, they say that they choose that angle because it's specifically because they work. So
Because they give the
because they
if you use
so I think they tried a lot of them and then they say, oh, this one seemed to work.
that's I mean if we had another value here, Pratush, if we change the value of cos theta, remember mu is cos theta, right? And last time we said, oh, so what angle is this theta? I thought it was pi thirds, but you were right, it's 54 something.
yeah, 54 point.
Yeah, okay. I suppose we change this to 1/2. You know, why not? We could use any other direction. Yeah. If we use 1/2, then these coefficients change. When you calculate the moments, you could use 1/2 here instead of 1 square root 3, and you'd have different coefficients here. Okay. And so the relationship between K and J would still be similar, but you wouldn't get this factor of 1/3. You'd get maybe 1/2, or it depends on the angle you choose, but it's not going to be 1/3. We get 1/3 here because it's what Felipe says, because it works. Because I mean, we put 1 over square root 3 here because it gives us 1/3. Did I understand your question?
But it's not satisfying. Yeah, this the other right is not satisfying to me, at least. I don't like. So
Let me put it differently.
so it seems like more trial and error type of thing, and it's not looks like a more general case. It looks like just we are looking into a one specific case, and that specific case is working fine. That that is the impression that I get from this assumption.
Yes, this is the correct impression. This is not a physical, a physically useful specific intensity field. It is a mathematical trick. Okay. We're saying, let us consider that the whole specific intensity field, as the book says, the book, what the book says, let us, where is it? This can be done, but here we use it. Just assume that the entire radiation field can be represented by just two angles, okay? So it means that we are in this situation where the specific intensity field is described by the two cones, okay? But really, we know that we're solving a uniform slab, and that the radiation intensity is not this one, okay? So that's kind of confusing, okay? And in many ways, the boundary conditions will be obtaining are not very satisfactory, but it's all we have to do analytical research, okay? So let's just for now convene that this is a mathematical trick. Let's see what happens, okay? So I'm saying, let's consider this specific intensity field, okay? And I'm using, right this angle, the cos theta is 1 square root third, okay? That's important because then these coefficients come out just right. As Felipe says, it gives me the right coefficients. Because with this 1/3, I get the one third here, which is what I need to say that the two cones fulfill the Eddington approximation. Okay. And so the two streams are solutions of equation 71, which is the one we're trying to solve, which is we need the boundary conditions for equation 71. So that this is the problem, right? We need to know what is J here and there. Okay. So yeah, I can always say that there's nothing coming from infinity towards a slab, okay? But the slab itself is shining in a non-trivial way. So what are the boundary conditions there, and so the idea is then, I got lost here. Okay, this is it. Okay, so we use the Eddington approximation in equation 69, which is this one. So that's equation 69, maybe. Let's go back a little bit. So these are the moments of the radiation transfer equation. Okay, so the moment 0 gives us 68. Moment 1 of the radiation transfer equation gives us equation 69. This is moment 1 of the radiation transfer equation. So this is the radiation transfer equation, equation 67. I take the first moment and I get to equation 69. Okay, that's the first moment of the radiation transfer equation. Okay, so that's the first moment of the radiation transfer equation, equation 69. Okay, and I plug in the Eddington approximation on the left-hand side. So we have H nu is 1/3 of the gradient of J. Okay. And so we can, yes, we solve for, we use this equation and equation 73. Maybe I should write it down. So we use this equation. Along with equation 73. Let me see if I can keep this in. So, okay, I'll put them there. Okay. So this is J nu is 1/2 I plus I minus. H nu and let me see, I have this one and I need one more. So can you, do we need can you? Maybe not. Oh yes, I need can you. So I need this one. Okay, and then I have this equation here, and I have this other one, and I have
Professor, I think h nu will be 1 by 2 root 3 into I plus minus I minus.
oh, I made a mistake here. Let me see. Maybe I've got a sign wrong here, sign Pratyush.
Yeah, yes. It for h nu one, it should be minus. Yeah, I plus minus I minus.
Thank you very much. Let me correct this immediately. Okay, so we have two equations here. We have equation, let me put the colors. So we have equation 1, equation 2, okay? And I replace the values for J, H, and K into equation 1 and 2, okay? Then I can solve I plus in terms of J, and this is what's done here. The result is this one, okay? So we have two equations, 1 and 2, that relates I plus and I minus with J. Okay, basically I have replaced, here I'm replacing this one with 1/6 I plus I minus, and that one with 1/2 square root 3 I plus minus I minus, okay? And here too. Okay, so we have two equations that relate J and I plus and I minus, and I solve for I plus and I minus, okay? And then I go back here and I say, well, if these were two streams, then the amplitude of the streams going downwards here should be 0 if no radiation is coming from plus infinity. Okay, so let me draw this here. I'm saying that in this position, these are the two streams. I'm trying to go through the origin. There. Maybe something a bit messy. Okay, and this other one. All right, it's not easy to draw on a tablet. Okay, more or less. So the amplitude here would be I plus, and that would be I minus. Okay, so this is the radiation intensity field going towards minus Z, and that would be the amplitude going to plus Z. And so in this point here, we know that I minus should be 0. No radiation should be coming from plus infinity. Okay, so if we are right at the edge of the slab, all the radiation there is coming from inside the slab. Likewise, if we're here at 0, okay, so we have radiation which is I plus here in 0, and we have another cone which has got the same opening angle, but a different amplitude, which is I minus at 0. Okay, so in 0, there should be no radiation coming from minus infinity. Nothing is coming from away. It's only all that's shining is this uniform slab. So I minus is there, but I plus is 0. But the problem is that, of course, the specific intensity field is not a two-cone. It's more complex. Okay, that's where we have an approximation. We're saying, okay, it's not the case, but for the sake of finding a boundary condition, we'll assume that at least in the borders, something like this must be happening. Okay, this is where the mathematical trick is connecting physics. Okay, we're saying that there should be no radiation coming from minus infinity. So this component here for the two streams should be 0. Okay, and so the boundary condition at 0 should be given by these requirements. So I plus in 0 is 0, and I minus in at this coordinate in L, which I call tau 0 here, or tau naught should be 0. Okay, so nothing should be coming from plus infinity. Okay, and so when we go back here and we say, well, this is 0, I plus is 0 at L, and I minus, no, that's the other way around. I plus is 0 at 0, and I minus is 0 at L. And so at 0, we put a 0 here, and we connect J nu with this gradient, and that would be the boundary condition at 0, and that would be the boundary condition at the other side. Okay. Now, the trouble is, of course, again, that this is okay for the two streams. Real life is different. Real life, we know that the radiation intensity here is not the two streams. Okay. So really, this is an approximation over an approximation. Okay, to get the boundary conditions. But this is all we can do. I mean, it's a difficult problem. Radiation, the analytical solutions to the radiation transfer equations are difficult. We have the uniform slab, and we have the Eddington approximation. And to solve the radiation, the differential equation for J, we need boundary conditions. And for those, we need another set of approximations. And this is one example where we have the two stream boundary conditions. So this is it. We finished chapter 1. Okay.
Professor?
This is well an important milestone.
Do you hear me?
I can hear you, Andres.
Okay. When we assume near isotropy, can we use higher order terms and get any better solution? Or get solutions at all?
We need to find a closure relationships. You could go higher. In this expansion, you could include a full spherical harmonics expansion. You must remember from your lectures in quantum mechanics and electrodynamics that we often use multiple expansions to solve differential equations, right? And the difficulty is in knowing where to truncate the series. Okay. So this is a solution. I've never seen higher orders here, but I'm sure that someone must have studied it. Okay, I'm not myself. I'm not an expert in radiative transfer as such. I use it for my research, but I don't go much beyond this. Okay, I use this is the most complex analytical solutions I use, but when it gets even more complicated than this, I just drop any analytical solution and I do it numerically. Okay. I was hoping that Rafael should be showing you his work, because Rafael uses numerical solutions to the radiative transfer equation, so you have an idea of how this is done. So guys, I think now is the time to really hand in your homeworks for chapter 1, so we can get on with chapter 2 now. Okay. So next Tuesday we'll be continuing the lecture with chapter 2, and so please hand in your homeworks as soon as you can. Okay.
Professor,
Okay.
where should we submit the homework?
Where should we send it? I think we should send it to Rafael.
Send it to Rafael. So his personal email, no, from the, we should be able to send him an email from the Ucursos, right?
Yeah.
Okay.
You can.
Thank you. I will.
Either write to him. It doesn't really matter. You can send him an email by Ucursos or just directly to his personal mail. I think it doesn't really matter. You know.
Okay, thank you.
And how is that doing? I mean, do you think you can have it all done by next Tuesday? Yeah.
Yes.
Yes, no problem. I had problems sending in today, but yes, Tuesday will be fine.
Okay, if you have any issues, remember you can ask questions to Rafael or to your fellow students' comments. Okay. Bueno, muchas
Yeah,
gracias.
we are cooperating.
I misheard, Pratyush.
I said we are like discussing with each other as well. So yeah.
Yes, we are
We
collaborating.
are on the same.
Oh, you are perfect, excellent.
Yes.
This is science. We need to start
Yes,
collaborating.
collaborating.
Nowhere. Chao, que le vaya bien.